Hi everyone. Today we are going to discuss educational codeforces round 190, problem D. In this problem, Alice and Bob are going to watch a TV series consisting of n episodes, numbered from 1 to n. Now, on ith day, so there are n episodes, 1 to n, and on ith day, ith episode will be shown in Alice City and bith episode in Bob City. So basically, let's take an example. Say so let's say on day one, episode one is shown in Alice City, also episode one is shown in Bob City. But in day two, episode three is shown in Alice City and episode four is shown in Bob's City. But on day three, episode two is shown on both city. On day four, episode one is shown on Alice City and episode three is shown on Bob City. And on day five, episode four is shown on Alice City and episode two is shown on Bob City. And like this. Now, that's basically this part says. Now, they plan to select a segment of days to watch the series. Initially, neither of them has seen any episodes. So, in each day, the following happens. So, in each day, in the segment they choose. So, basically, Alice and Bob will choose some segment L from L to R. And on each day, what will happen is uh, let's choose another L. So in each day, what will happen is if Alice has already watched episodes from 1 to A of I minus 1, but not A of I, then she watches A of I number episode. Otherwise, she watches nothing. And same goes for Bob. If he watched episodes from 1 to B of I minus 1, and but not B of I, then he watches BI, episode BI on day I. Otherwise, he watches nothing on that day. And more importantly, okay, let's clear this part first. So let's say for Alice, the episodes shown in order are like this: 1, 2, 1, 3, 2, 1, and so on. Now, on day one, Alice shows episode 1. On day 2, Alice does not see episode 3 because he hasn't seen episode 2 yet. So on day On day 2, he skips the episode, but on day 3, he watches episode 2. Now, on day 4, he skips episode 1 because he already watched episode 1 and so on. And same logic goes for Bob as well. So this is one condition, basically this part. And what this part says is that either both of them watch the same episode on any day, or neither of them watches anything of that. So this part actually means that if if Alice watches episode 1 on day 1, then Bob also watches episode 1 on day 1. And and if Alice watch, let's say, if Alice watch episode uh, 2 on day 3 and Bob doesn't watch episode 2 on day 3, let's say he watches another episode, then actually uh, Alice would watch episode 2 and Bob won't watch episode 3. So this won't be a valid this won't be a valid choice of LR if this sort of thing happens. So we have to choose L and R in such a way that in such a way that Alice and Bob watches same episode on same day. We have to fulfill this condition, and to fulfill this condition, how many LR we can choose, L and R pair we can choose, how many subsegment of days we can choose so that this condition holds true. Understand the problem? For example, on this example, 1, 2, 1 is for Alice, and for Bob, it's 1, 2, and 2. So it's day 1, day 2, day 3. Uh, Right. So one valid choice is that this is our range. This is our L and R both. So if this is our range, then it's a valid range because for this range, Alice watch this episode and Bob watches this episode, right? And nothing else. So this condition holds true. Now for this range, Alice and Bob both watch this episode, then Alice and Bob both watch this episode too. So this is also a valid valid segment. But there's another valid segment which is no let's see. Okay, yeah, this is also a valid segment because they both watch 2 movies in the first 2 days, and on the third day they don't watch at all because they have already watched 2 movies. So there we have 3 subsegments. Also, there is another L and R we can choose, is that we can choose only this. So if everything starts on, so if our subsegment was like this, then Alice would start here and Bob would start here. Since no one actually watched movie 1, then no one would watch movie 2. And this would still not violate this condition because the condition says Alice and Bob watches same episode on same day. And since they are watching no episode, so they are basically watching same episode on the same day. This condition holds true. So we have to find L such so how many L and R we find in this range? Number of L and R is basically 4, right? So we have to calculate the number of valid subsegments. How do you solve this problem? Uh, we can solve this problem. We can try this problem with brute force at first. Brute force. So how would be the brute force look like? let's say in a sequence, we actually fix an L for our subsegment. So if this is where we start, this is where we start choosing the days for Alice and Bob, then what is the maximum? What is the maximum value R we can choose? Because if we can choose, one thing to observe is that if we can choose, if Alice and Bob, if we can choose R L to R for Alice and Bob, then we can also choose L to R minus 1. Because if this part is a valid subsegment, then this part is also a valid subsegment. So in our brute force approach should look like this. Uh, for each L, let's say this is our L, and Alice and Bob actually watch episode on. This is where they watch their first episode. Good. So this part is valid. Then this is where they both watch their second episode. So we can extend this partition up to this index, and we'll do this until we can't. So let's say if next for the next episode, episode 3 is here, but here is episode 4. So after Alice watches episode 2, he can watch episode 3, but the day Alice watch episode 3, Bob actually cannot watch episode 3 because there is no episode 3 on that day for Bob. So we can't really extend this up to this. We have to extend this up to this. So this this would be our right. So for each index, we can do this until we can't extend anymore. And our once we find our result will be our let's call this position R. So we are taking R is the R. Let's call R the position where we stop. So we take from L to R this range. So the total number of subsegments we can choose. So R is our maximum for L. So total number of subsegments we choose is R minus L because we can choose this up to R minus 1, right? What is the complexity? The complexity is for each L, we can, for each L, we are actually fixing our L at each index. So first of all, we are thinking our L is 1, then L is 2, then we're fixing our L at 3, and so on. So it's basically O of n, and for each L, we are finding 1, then we are finding 2, then we are finding 3, and so on. And at most, we need to find n numbers. So we also have O of n operations for once we fix n. So our overall time complexity becomes O of n squared, which is too slow for this algorithm. It would be fast. So how can we make it fast? It can be fast if from this index, we can already know it would stop at here for this index instead of from this index, then go to this index, then go to here, we can already tell from this index that it would stop here. We need to do, we need to calculate this. We need to know, we need to know this for when we, for this index. Instead of looping through 1 to 3 like this, when we are at 1, we want to know where it would stop in one time. How do we do this? Of course, we are going to use dp. So now, how can I use dp? Before we go to the implementation, let's define some terminologies. So we define dp of L. So if we at this index L, if we at index L, then we define dp of L. So what is dp of L? dp of L means, let's say at L, there is some number x. Okay. We imagine that considering that at L, Alice and Bob both watched some episode and it's episode X. Then what is the rightmost index? The range can extend from L. That is dp of L. So for this, if at L, Alice and Bob have watched episode 1, then actually, like our previous example, this example, dp of this index is also dp of this index, because 2 also stops this index also. If you start here, it stops here, and if you start here, it goes here and then stops here, so it also stops here. So if we have x at, if Alice and Bob both watched episode X on day L, then if they watch the next episode, which is X plus 1, if they watch both, watch the X plus 1 episode on the same day, then dp of L is actually, let's say it's position of X plus 1. So it's dp of position of X plus 1. So basically dp on this value is the same as dp at this index. dp at this index is the same as dp at this index, but it will only happen if they are equal. What if they are not equal? What if at L we have this, and for A it's X plus 1, but where A finds X plus 1 episode, B does not find it, so they are not equal. What will happen then? What will happen is, basically, let's call this Basically, dp of L, since this would stop right here, so this is the base case. So base case of the dp. So this part. So how do we compute this part? To compute this part, we actually need to know that the, let's call position of A of x plus 1 as the last position, right? Next position, next position of x plus 1 in A, and P of B, PB of x plus 1 will be next position of this in B. So the next number is x plus 1. So we might find x plus 1 for array A before we find x plus 1 for array B. In this case, or vice versa can also happen. We can find x plus 1 somewhere before than A for B. That's why we need to dp of L would be minimum of, you know, where we find x plus 1 in A and where we find x plus 1 in B. So this would be the base case for the dp. Got the idea? So basically, yeah. So when we fix some L, when we fix some L, we actually calculate, and we watch episode X. Here we define dp of L, but dp of L actually needs that we take some value from dp of L prime, but where L prime is greater than L, because we always take from right value from left value. So we need to iterate from right to left for L instead of left to right, because to calculate dp of L we need to dp of some right value, evaluate the right. So there goes our dp of L. Now, how do we calculate exactly the R for this L? Notice that when we are at L, we might not, we may have some element x and y here. They might be equal or not. But when we are at L, we need to find 1 first, then 2, then 3, and so on until they don't match. Let's say they have U and here V, until they don't match. So we actually need to calculate dp of L, considering that this value is actually 0, 0. Because if these two values are 0, we are going to find our x equals 0, then our x plus 1 will be 1. So either we take the dp value we calculated here, or we take this part to find our R. And once we find our R, we add this R minus L. That is the number of our subsegments that starts with L. That's it. That's the logic. If you have any confusions, please let me know in the comment section. And let's see the code. Yeah. So this is, we defined our arrays and position of A and position of B array, and we defined our DP. We initialized by n because until if they don't stop, then rightmost value is n. So we iterated L from rightmost to leftmost. We updated the last position of each array. So we update the last position of the current value of A and the current value of B. Then if they are both equal, then we actually calculate DP using our formula, using these two formula, this and this. Then R is basically this calculation, but with x equals 1 and result, updating our result. So that's it. That's our whole solution. It's pretty complicated, but if you just it's not that hard, but the intuition is quite difficult. So hope you enjoyed. See you in the next video.